Section: Introduction. In this section, we will discuss recent advancements in large language models, LLMs, that have mainly focused on a few data-rich languages, such as English, leading to a bias in these models. This bias makes it challenging for LLMs to work effectively with languages like Hindi, Arabic, Bengali, and Japanese, which have large speaker populations but are underrepresented in the training data. Our goal is to address this bias and improve the capabilities of LLMs to perform well in various languages. We aim to bridge the gap between the demand for multilingual models and the current limitations in the field. Large language models like GPT 3.5 and BERT have transformed artificial intelligence by enhancing natural language understanding and generation. However, these models are primarily designed for English, limiting their usefulness across different languages and cultures. Multilingual LLMs have been developed to tackle this issue, but they often struggle to balance performance, efficiency, and scalability when dealing with a wide range of languages. The development of SUTRA was driven by the shortcomings of existing multilingual LLMs. Language-specific models like HyperClova and OpenHATI are costly and challenging to scale, while traditional multilingual models like Bloom and Llama 2 face difficulties in handling multiple languages effectively. SUTRA was created to overcome these challenges by separating concept learning from language learning in its architecture. SUTRA is a unique multilingual LLM that focuses on universal concepts independently of language, using specialized neural machine translation mechanisms for language-specific tasks. By employing a mixture of expert strategy, SUTRA enhances efficiency by involving relevant experts based on the linguistic task at hand. These models are internet-connected and can provide up-to-date information without losing their multilingual capabilities. Through a combination of multilingual skills, online connectivity, and efficient language generation, SUTRA aims to redefine multilingual language modeling. In the following sections, we will explain the architecture of SUTRA, our training approach, and present evaluations demonstrating its superiority over other multilingual models on various benchmarks. By separating concept learning from language processing, SUTRA offers improved accessibility and performance across diverse linguistic contexts. Section Summary. In this section, we address the significant bias in large language models, LLMs, towards English, limiting their effectiveness in languages with large speaker populations like Hindi, Arabic, Bengali, and Japanese. To bridge this gap, we introduce SUTRA, a novel multilingual LLM architecture that separates concept learning from language learning, enhancing scalability and performance while preserving linguistic nuances. By leveraging a mixture of experts, strategy, and internet connectivity, SUTRA promises to redefine multilingual language modeling by improving efficiency and language generation across diverse linguistic landscapes. Section: Related work. In this section, we delve into the advancements in large language models, LLMs, and their multilinguality aspects. We have seen significant progress in LLMs with models like GPT-3 and BERT, which excel in language understanding and generation by learning complex patterns from vast amounts of data. However, these models have mainly focused on English language data, prompting the need for multilingual LLMs to support global linguistic diversity. Pioneering works such as MBERT and XLMR have shown promise in learning representations that can generalize across languages, but they encounter challenges in balancing performance across different languages, especially those with limited representation in training datasets. As the number of languages increases, the scalability and efficiency of these models tend to decrease, requiring specialized architectures to effectively handle language diversity. Neural machine translation, NMT, has played a crucial role in enhancing multilingual model performance. Early NMT systems faced limitations in architecture complexity and translation quality, particularly for low-resource languages. Recent studies have revisited key challenges in machine translation within the realm of advanced LLMs. These studies shed light on persistent issues like domain mismatch, rare word prediction, and translating long sentences, despite significant improvements in these areas by LLMs. The translation performance of LLMs has been explored from the user's perspective, emphasizing their potential to improve the translation of long sentences while also recognizing challenges related to domain mismatch and rare word prediction. Google's neural machine translation system has set a benchmark for progress in bridging the gap between human and machine translation. Additionally, the mixture of experts architecture has shown promise in enhancing translation performance for various low-resource languages. Mixture of experts, MO, has emerged as a valuable architecture for managing computational costs in scaling up LLMs. Recent studies have highlighted the benefits of MO, such as dynamic data allocation among experts to achieve model sparsity and optimize performance. The application of MO in open pre-trained transformer language models has led to efficiency and scalability improvements compared to dense models. Moreover, MO has shown potential in enhancing language understanding tasks, as demonstrated in studies focusing on Chinese idiom datasets. Researchers have also explored multimodal LLMs capable of processing and generating content across different modalities like text, images, and video. These models have shown promise in tasks such as image captioning, visual question answering, and computational linguistic phylogeny by leveraging cross-modal information to enhance performance. Integrating visual information into language models has proven beneficial for improving translation quality in multimodal machine translation. Modern LLMs like Llama 2, GPT 3.5, and GPT-4 have been developed as open-domain chatbots capable of engaging in extended dialogues on various topics. However, a significant limitation they face is their time-locked data, leading to potential inaccuracies in responses due to outdated information. Efforts to rectify this issue include additional training with human feedback and incorporating real-time data through in-context learning. SUTRA presents a structured approach for response augmentation, enabling the model to learn, reason, and interpret information from diverse knowledge sources effectively. Section Summary. In this section, we explore the advancements in large language models, LLMs, like GPT-3 and BERT, emphasizing the shift towards multilingual models such as MBERT and XLMR to address global linguistic diversity. Neural machine translation, NMT, has played a crucial role in enhancing multilingual model performance, with recent studies focusing on challenges like domain mismatch and rare word prediction. The emergence of mixture of experts, MO, architecture offers a promising solution for scaling up LLMs efficiently, while researchers are also investigating the potential of multimodal LLMs and addressing limitations in online LLMs related to time-locked data and knowledge cutoff dates. Section: SUTRA Approach. In this section, we introduce the SUTRA approach. SUTRA is a unique multilingual large language model architecture that separates concept learning from language learning. This approach is inspired by how humans learn, where understanding core concepts precedes language acquisition. By decoupling concept learning from language learning, SUTRA becomes scalable and can cater to a wide range of languages. Our training methodology consists of 3 phases: concept learning, language learning, and language alignment. In the concept learning phase, the core model is trained to grasp basic concepts in a few languages. Simultaneously, we train specialized neural machine translation (NMT) encoders and decoders, along with a multilingual tokenizer, to ensure consistent translation across languages. The final phase involves merging concept understanding with linguistic proficiency. The architecture of SUTRA is based on the transformer architecture with enhancements that allow for a longer context length and the use of MO layers for efficient computation and memory usage. The model utilizes an expert mixture module that combines outputs from different expert networks based on a gating function. This function selects the top experts for each token, optimizing computational resources. Our language training strategy focuses on leveraging linguistic similarities during the learning phase. We use a diverse dataset, including real and synthetic conversations in multiple languages, to train the model comprehensively. By incorporating abundant data from languages like English, we enhance concept learning. Additionally, we use a combination of real and synthetic data during language learning and alignment to strengthen our training framework. To ensure balanced representation across tasks and languages, we translate instructions and data using Neural Machine Translation, NMT. Our training dataset comprises over 100 million samples from various languages, including English, Hindi, Tamil, and Korean, sourced from different datasets like SUTRA, FLANV2, Open Assistant, and WikiHow. The dataset includes long-term conversational data to improve human-AI interactions. Overall, the SUTRA approach aims to create a scalable and multilingual language model by decoupling concept learning from language learning and leveraging diverse datasets for comprehensive training. Section Summary. In this section, we introduce the SUTRA approach, a novel multilingual large language model architecture that separates concept learning from language learning, inspired by how humans learn. By decoupling these processes, SUTRA becomes more scalable and can easily accommodate a larger number of languages. The training methodology involves 3 phases: concept learning, language learning, and language alignment, with a structured inference path through NMT encoders, the concept model, and NMT decoders. Section: Training multilingual tokenizers. In this section, we focus on training multilingual tokenizers. Tokenization is a crucial step in natural language processing, NLP, where text is converted into a sequence of tokens representing subwords or words. While English tokenizers can work for non-English languages, they may not capture language-specific nuances efficiently, especially for non-Romanized languages like Indian languages such as Hindi, Gujarati, or Tamil. Tokenizers from popular language models like Llama 2, Mistral, and GPT-4 split words in Indian languages into 4.5 to 8 times more tokens compared to English. To address this, we aim to reduce the average number of tokens a word is split into by a language model on non-English text, known as token fertility. By training a sentence-piece tokenizer on a large multi-language dataset and combining it with a pre-trained English tokenizer, we achieve a significant reduction in the number of tokens consumed across languages, leading to more efficient and semantically meaningful text generation. We then evaluate our model on various natural language understanding, NLU, and natural language generation, NLG, tasks, including the Massive Multitask Language Understanding, MMLU, benchmark. This benchmark assesses the knowledge and reasoning abilities of large language models, LLMs, across 57 subjects spanning STEM, humanities, social sciences, and more, ranging from elementary to advanced professional levels. It tests both world knowledge and problem-solving skills, ensuring models can generalize their understanding to new domains. To extend our evaluation across multiple languages, we develop a multilingual assessment framework focusing on English, Korean, Japanese, Arabic, and Indian languages. Our model, SUTRA, demonstrates consistent performance across languages, outperforming other models like GPT-4 and Llama 2, particularly in languages less represented in language models such as Hindi, Gujarati, Tamil, and Korean. This universal approach makes SUTRA a robust solution for global applications in business, education, and cross-cultural communication, setting a new standard for multilingual language models. Section Summary. In this section, we focus on training multilingual tokenizers to address the inefficiencies of English-specific tokenizers in capturing language-specific nuances, especially in non-Romanized languages like Hindi, Gujarati, and Tamil. By reducing the average number of tokens a word is split into, our tokenizers lead to a significant reduction in overall tokens consumed across languages, enhancing inferencing efficiency and semantic meaning. Our SUTRA model demonstrates consistent linguistic performance across various languages, showcasing robust multilingual capabilities critical for global applications, unlike other leading models that often struggle with non-English languages. Section: Comparing with leading models for multilingual performance. In this section, we evaluated various state-of-the-art models on the multilingual MMLU benchmark. We compared models like GPT-4, GPT 3.5, Mixtral, Llama series, Perplexity, Hyperclova X, and Airavata model. Some of these models are generic, while others are specifically optimized for certain languages like Korean and Hindi. Our SUTRA models showed promising results, matching or even outperforming GPT 3.5 and Llama 7B in two related tasks, especially in providing natural responses across different languages. Despite GPT-4 being the top performer, its high cost limits its widespread use in cost-sensitive markets. The SUTRA models excelled by 20 to 30% in multilingual performance on the MMLU benchmark, demonstrating their ability to understand and generate responses in various languages, even outperforming models tailored for specific languages. Furthermore, our SUTRA models are real-time, fact-based models that give informative responses in a conversational manner. They continuously update their knowledge from the internet to provide the most current information. These online models can answer time-sensitive queries accurately, going beyond their initial training data. In evaluations using the Fresh Prompt Framework, SUTRA online models surpassed competitors like Google's search engine augmented models, GPT 3.5, and Perplexity AI. The benchmark covered different online scenarios with never-changing, slow-changing, and fast-changing answers, and SUTRA performed well across these scenarios.